Hi, this is Kona, and talking about a linear, so what's covered in Unit 5, which are linear regression. So part of that is correlation, and then a simple linear regression. So a correlation is just a measure of strength and the direction of a linear, so straight line relationship. It's used when we have paired numeric data, so it has to be paired, and it does have to be actual numbers. So example, a person's weight and their height, or a person's age and their IQ. So it's paired, and it's two different variables that are both numbers. So really big here though, correlation does not equal causation. Correlation simply describes the relationship between two variables, does not explain why the two variables are related. A correlation can't be used or interpreted as proof of a cause-effect relationship between the two variables. So really important. You can't prove anything. It doesn't mean this causes this. It just means that they're related and how strong they're related, or the direction of their relationship. How we normally visualize this is through a scatter plot, which is a graphical representation of the two variables. We've got the two variables are your explanatory, which is your X independent predictor one, which attempts to explain or predict the outcome, and the response variable, or the Y, which is your dependent and the measure of the outcome of study. In some cases, you might not you might just think two things are related and you're curious how strong or in what direction they're related. So you might not really have an explanatory response. I mean, so weight and height, maybe you do have an idea. Maybe you think heights, people who are taller weigh more. Well, in that case, the height is going to be your explanatory, because you're thinking it's explaining the response variable of weight. Age and IQ, maybe you think the older someone is, the higher their IQ. So in that case, age is going to be your explanatory that you think explains or predicts the response variable of IQ. So just kind of an example there. Correlation coefficient is actually what you use to measure a correlation. It measures the linear association between the two variables, the explanatory and the response. Is also considered a measure of the correlation between the two quantitative. Possible values have to fall between -1 and +1. So this is really important. -1 is just as strong as +1. The only difference is the direction, which we'll get to a little bit lower. So 0 is the weakest relationship, but it can be like a -0.2 and a +0.2 are both equally as weak, because it doesn't matter which side. So this is almost kind of like an absolute value thing. So don't think of it as -1, oh, it's a stronger, weaker relationship, and +1, it's a stronger, positive relationship, or a strong relationship, and this is a weak relationship. Weak is close to 0, strong is close to either +1 or -1. So negative correlation, and these negatives right there are considered the R value. So this would be an R value of +1, R value of -1, R value of -0.5. So those would be R values, or correlation coefficient values. Something to keep in mind, outliers are extreme data points that don't seem to fit with the rest of the data, and they can have a dramatic effect on the value, the R value of a correlation. So just kind of keep in your mind. Characteristics, correlations measure three characteristics of the relationship between the two variables. First of all is the direction of the relationship. So in this case, you can have a positive, and with positive correlation, which means your R is positive, which means it's going to be over here on this green side. The variables move in the same direction. So when X goes up, Y goes up. So here you can see X is up high and Y is up high. It also means when X is down low. So here's when X is low, Y is also low. So positive just means they're both going in the same direction. Whether it's both high or both low going down, it doesn't matter. It's that the variables are moving in the same direction is what makes this positive. So what makes a positive correlation is that the variables are going in the same direction. That's really important, because what makes a negative correlation, so this would be a negative R value, is that the variables are moving in the opposite direction. So when X goes up, Y actually goes down. So here X is high, but Y is actually low. And here, when Y is up high, X is low. So negative correlation, all it means is that the variables are going in opposite directions. Positive means they're going in the same direction. No correlation means that there's nothing going on, and there just doesn't seem to be any relationship here at all. So nothing. This means it would be, the R would be very close to 0 for this one. So looking at the actual strength of the relationship, and that is measured using that correlation coefficient, so that R, So the closer r is to +1 or -1, the stronger the relationship between the variables. The closer to 0, the weaker the relationship is between the variables. When looking at a scatter plot, when the data looks closer to being in a straight line, it will have a higher r value, so closer to -1 or +1. Data that isn't close to forming a straight line is all over the place will have an r value closer to 0. So here you can have a perfect positive correlation. So here's a +1, and see it's very close to being a straight line going in this direction. A high positive correlation, so this is an R value of 0.8, you can see it's not a perfect straight line, but it's pretty close. Here's an example of a low positive correlation. Well, it looks like it's kind of going in the general direction, right, of a positive, but it's not nearly as close as this. And then you've got the no correlation, which is just all over the place. So low negative correlation, the data looks similar to the low positive, but you can see that it's going in a different direction. This is one high, one low. This is high and high, low and low together. High negative correlation, it's kind of going in that direction, and it's just getting closer and closer to that -1, which is that perfect negative correlation. So basically, the closer the data is to forming a straight line, the higher that R value is going to be. Higher meaning either -1 or +1. Okay? So the form of relationship normally refers to how linear, so how straight of a line the data is. So in the example figure above, the stronger the correlation, so closer to 1 or -1, I keep forgetting to put the positive. +1 or -1, the more the data seems to form a straight line. The lower the correlation, and I'm actually going to change that to weaker. Weaker the correlation, closer to 0, the less the data seems to form a straight line. This is normally determined from the line of best fit. The line of best fit is a straight line that represents the data on a scatter plot. The line may pass through some of the points, none of the points, or all of the points, just depending on how good the fit is. And we're actually going to do that a little bit more simple linear regression, but an example here, and if you've probably done this in a class before at some point, let's see, shapes, a line. So in class, you might have had to draw a line of best fit. So see how this one, basically I can draw my line there and it's like perfect. Here, if I draw my line, I have to go back to insert, I guess I do. All right. Okay, so here if I draw my line, see how it's not fitting all of the data points? So it's coming close to fitting the data points. So they're kind of close, but they're not right on. So this is why the correlation isn't quite as high as this one, because it's not forming that straight line. So then if I come over here, do it again, and here we go, and you can see it barely hits all of them. So see how the further the data points are away from that line of best fit, the lower the correlation is, and it doesn't matter. So here, it doesn't matter whether it's a negative or a positive correlation. What it has to do with, and actually that's not a very good line. It's probably better. It just has to do with how closely the data points form or fit to that straight line. In some cases, you can kind of eyeball it and just kind of say, okay, yeah, that looks like a low. This looks like a high negative correlation. But if we really want to know exactly and get that true, what is the actual line of best fit for these specific data points, we actually use the simple linear regression. So a regression uses one or more explanatory variables to predict one response variable. This is done by finding the line of best fit for the variables. And a simple linear regression just involves the one explanatory variable, where the multiple linear regression, which we'll be doing later, involves two or more of the explanatory variables. So for the simple linear regression equation, we've got kind of our y hat here, which is our response variable, and that's the mean of y for a given value of x. And that's equal to our y-intercept plus slope times our x variable, where our y-intercept is the mean, and actually that needs to be equal to mean y minus slope times mean x, where our slope is equal to that r value, so remember our correlation coefficient, times the standard deviation of y over the standard deviation of x. And our explanatory or predictor variable is just an x variable. The test statistic for our linear regression, because we will be doing a test statistic in order to find a p-value, the t, which is our test statistic, is just that r, correlation coefficient, over the square root of 1 minus r squared over n, meaning the number in the sample, minus 2. And when are we going to use a regression? Before a regression is done, the correlation should be checked to see if there's any correlation or not. So if there's not a correlation, then there's really no reason to do a regression. If there is a significant linear correlation, so p-value from the correlation is less than or equal to 0.05, then you can perform the regression analysis to find the equation of the best fitting line. So that's pretty much it, and we're going to move along and do some actual examples of the linear regression stuff.